Assalamualaikum and hi guys. So in this video, basically we will just continue the previous video on part A. So basically this is part B, where we will be focusing on the step for generation of molecular structure and also feasible mixture. Okay, so first we will look at the generation of molecular structure. So what is the objective of this step? So the objective is that having or given the functional groups as building blocks and a set of rules which will advise us to combine the functional groups into chemically feasible molecules, then we generate the candidate structures. Okay, so basically the rules are implemented in order to limit the combination of groups, so that only those which are chemically feasible molecules can be generated. And of course, the number of feasible molecules would be fewer than the total number of combination where there are no restriction. Okay, right. So example. So let's look at an example here. Okay. So given the groups CH3, CH2, and OH, so we have three functional groups here or building blocks. So how many chemically stable molecules can be generated? How many chemically stable molecules can be generated with a minimum of two groups and a maximum of three groups? And of course, you should understand that the same type of building block can be used to more than one time. Okay, unless it is mentioned otherwise. For example, here and the condition that the OH functional groups appears no more than one. So it means that in all the uh, generated or the feasible, chemically feasible or stable molecules, we don't want any molecules which have OH atoms more than one. So basically, that's the limitation that we set. That's the limitation that we set because that is our requirement. Okay, so I give you some time. Okay, or maybe you can. I think it's better if you can pause this video. Okay, I hope you can pause for a second. Okay, maybe try. I want you to pause the video because I want you to try to find the answer based on the knowledge that you already have. Okay, so based on the given constraint, based on the knowledge that you have, please try to list down all the compounds. So okay, so I hope you can pause the video in 3 counts. 1, 2, 3. Okay, pause it and we will meet again after 2 minutes. Okay, pause. Okay, all right. So I hope when you play your video now is already 2 minutes past and you already have some answers. Okay, so let's see your answers. Is it these molecules? Okay, maybe you can check with your answers. Are these the chemically stable molecules? Are all does all the molecules listed here satisfies the constraint? Not all, right? For example, here we have OH and OH. So we have two OH atoms in OH groups in one molecule, whereby it is clearly stated here that no two OH can be appearing in one molecule, right? So this one is not counted. This one is not counted. What about this one? CH3, CH2, CH2. Can we use that? What about CH3, CH3, CH3OH? Is it does it satisfies the given constraint? Okay, so so basically the three compounds at the bottom is not chemically feasible and not according to the constraint. The first two, you know why? Because of the OH groups, which is appearing more than one. Yeah, because our requirement is only we want only one OH atom. One OH group in one molecule. What about this one? you have CH3. So C is connected with 3 hydrogen atoms and another carbon atoms, right? So if we recall back our knowledge on the valence electron, on the valence connectivity, we know that for carbon atoms have 4 valence electron, then it needs 4 more electrons for it to be stable, right? So if we assume one electron for one single bond, then of course carbon need to be connected with 4 atoms, right? So this carbon is connected with 3 and 1 atom, which is total 4. This carbon is connected with 2 hydrogen atoms and 2 carbon atoms, then the total is 4. But for these carbon atoms, only 3 bonds are connected to it, 2 from hydrogen, 1 from the other carbon. So this carbon is not stable because it has one free bond, right? So this also cannot be considered as chemically stable. So these 3 at the bottom are removed. So basically the one at the top basically satisfy all the constraint and also the even the valence the valence connectivity are also satisfied. So basically the list of the compound which are chemically feasible and satisfy the constraint can be easily obtained, right? Um, yeah, based on the knowledge that you already have. Why you can do it very easily? Why? Because you only have a small number of groups and there's a certain constraint which have been set. And that is why it's quite easy for you to generate the molecules which are considered chemically feasible or stable based on the valence information that you learn that you know before and also the constraint given. Okay. Okay, so what if we have many building blocks? We have many functional groups. It would be um quite tiring or quite and a daunting task in order to generate the feasible molecules, right? When we have like many function groups, because otherwise hundreds and thousands of different molecules which are chemically feasible can be produced, right? Therefore, we need to have a rule. Okay, so in order to ensure molecules which are chemically feasible, the following rules must be satisfied, and this rule is by Odell and Macchietto, 1993. At the end of the video, I will provide the list of the references that you can refer to if you need to know more detail. Okay, so there are 5 equations, there are 5 rules that we need to obey in order for us to consider the molecule to be chemically feasible. So this is the first equation, the second equation, the third equation, fourth equation, and the fifth equation. And let's look into more detail in terms of what are the meaning of those notations. Okay, so we have M here at the top. M is the number of distinct groups in the basis set. For example, like in the example previously, the M is equal to 3 because there are 3 different 3 distinct groups in the set. Okay, and then we have Q. So Q can be found in the first equation. So Q is equal to -1 if we want to generate bicyclic type of molecules. Q equal to 0 if we want to obtain monocyclic type of molecules, and EQ is equal to 1 if the type of molecule that we want to produce is acyclic. Okay, and then we have NJ and I. So index I and J is actually representing to the groups, different groups, and N is actually the number of the groups J and I which are present in the molecule. And then we have UJ. So UJ is the valence of group J. For example, carbon have 4. The valence for carbon is 4. The valence for hydrogen is 2. For example, valence for oxygen is 2, right? And then we have n max, which can be found in equation rule number 4. So n max is the maximum number of groups which are allowed, which we specify in the molecule. Like in the previous example, the maximum number of group that we set is 3, right? And n, so n is can be found in equation rule 5. So n is the number of group present in a specific molecule. And also for equation 3, we have NJL and NJU, and these are the lower and upper bounds which we specify in terms of the number of the allowed groups of type J respectively. So meaning that, for example, CH3, so what should be the lower and upper bound? CH2, what is the lower and upper bound, and so on. Okay. So this is the rules which each molecule need to satisfy. If the molecule satisfy all 5 rules, then only it will considered as chemically feasible. Okay, so next, let's see how we understand the rule, how we can understand how to use the rule by seeing by looking into more details on how the rules is implemented in the examples which is shown before, which is this one. So we recall back the example. Okay, so let's see how we can solve the problem using the rules that we have learned, discussed just now. Before that, you don't use any rules, right? You just use whatever based on the constraints given and whatever knowledge that you have before. But now we want to see how we can apply the given rules by Odell and Macchiato, and how we can prove that the list of compounds that we have listed before is indeed chemically stable or feasible. Okay, the solution. So basically, we first of all we list down all the compounds, the building blocks that we will consider: CH3, CH2, and OH. And then we set the lower sorry, this is the valence of each of the compound. For example, CH3, so CH3, so the carbon atom here need to only attach with one more single bond with one more molecule. It has one valence atom electron, then that is why the valence is 1 here. And then for CH2, there are 2 valence electron for atom carbon, that's why here is 2. And for H, so H already complete because it needs only one bond. For O, it needs it has 2 valence electron, so one of it have been shared with hydrogen, but there is one more which is free, so that is the number is 1, so that is why is 1 here lah. So I'm sure you get the point in terms of the valence is actually related to the number of electrons valent, yeah, which are still available. And this is the lower and upper bound. Okay, so for CH3 and CH2 we set the lower bound, basically for all compounds we set 0. So it means that in either one of the in any of the generated molecules, it is okay if we don't have OH, if we don't have CH2, and or if we don't have CH3, right? Okay, so if we don't have OH, then of course our compound will be just alkanes, for example. Okay, and the upper bound, okay, for CH3 we set it at 2, CH2 we set it at 2. Okay, and for OH, this one, it is visible from the equation. The maximum number of OH group that we want to have is only 1, and we are okay if you have more than 1 CH2, and the maximum is 2. Okay, so basically this is what we have set. Okay, so and then what else? Okay, and then we know that M is equal to 3 because there are 3 groups, and Q is equal to 1. Why Q equal to 1? Because we want to produce, okay, because we set it on our own. Okay, we don't want bicyclic, we don't want monocyclic, we want acyclic. So acyclic means that there's no there's no ring. There's no ring. Bicyclic, monocyclic, you have rings, right? We don't want ring, so that's why Q equal to 1. Acyclic. Okay, so n max is 3, right? So that's the upper limit that we set, maximum of 3 groups. We don't have to set n min. Okay, into more detail. So what we can do is that we can list down all possible molecules that can be generated. Okay? Of course, if we don't set any restrictions, then of course there are many possible molecules which are available. It's only that in this example, I only list down 1, 2, 3, 4, 5, 6, 7 different molecules. And if you look at the molecules, the maximum number of groups available is 3 and minimum is 2. Okay. And also here I include the group vector just to see the another representation of the structure. And then n is equal to 2 and 3 depending on the number. Okay, basically I have already mentioned the number. And then q is equal to 1 for all, right? And okay, when looking at this video, when looking at this table, please also refer to your book. Refer to your textbook. So if you refer to your textbook, okay, uh, okay, so if you refer to your textbook for equation number 1, so it's a summation of uh, summation of 2 minus uj, okay, multiply with nj equal to 2q, right? So the equation needs to be equal to 2q. So since q is equal to 1, then the equation needs to be equal to 2. Okay, and we need to sum that term for all the groups appearing in the molecules. But in this molecule, there's only one group, so that's why this term is only 1. So of course, you can use the information that we have defined previously. For CH3, Uj is 1, so 2 minus 1. So Nj is 2, so multiply with 2. 2 minus 1 is 1. 1 multiplied with 2 is 2. 2 is equal to 2. Then it satisfies the first rule. For the second one, so CH3OH, so there are two groups, right? So the first part is for CH3. Okay, 2 minus 1 valence for CH3 multiply with 1. There's only one CH3 uh, in this compound, right? Plus, next we calculate for OH. So 2 minus 1 valence for OH is 1 multiplied with 1. There's only one OH in this group. Okay, so 2 minus 1 is 1. 1 multiplied with 1 is 1. Okay, for the second term, 2 minus 1 is 1 multiplied with 1 is 1. So 1 plus 1 is equal to 2. So it satisfies the second the equation. So all these satisfy the one in black numbers are the one which have satisfies the rule. It's only that for equation for the last molecule CH2 CH2 CH3. So if we look at the group vector, we know that there are two different groups, CH2 and CH3. So as usual, we calculate one by one. So this is for CH2. So 2 minus 2 valence for CH2 is 2. So 2 minus 2. And since there are two groups, CH2 groups in this compound, then we multiply with 2. So 2 minus 2 is 0. 0 multiplied with 2 is 0. Right? And this is for CH3. So 2 minus 1 is the valence multiplied with the occurrences. There's only one CH3. So 2 minus 1 is 1. 1 minus multiplied with 1 is 1. So it's equal to 1. And 1 is not equal to 2. That is why this rule is not being satisfied by the molecule. Okay. And then for the second rule, so the second rule is okay, for the second equation, it can be confusing. So what it actually means is that we need to calculate one by one based on the compound whereby we set it as J. Okay, it's okay. We can try to look at an example. Okay, for this compound, so CH3 and CH3, and looking at the group vector, there is only one type of group vector. Since there's only one type, so rule number 2 is not applicable. It is only applicable if you have at least two different type of group vector, like the one for the second molecule. So for the second molecule, we have one CH3 and one OH, right? So first, what we do is that we set one group as the group J, one group as group J. For example, here we have CH3, right? So CH3, we set it as J. And then when we want to use the equation, so if you look at the equation, is Ni, right? So since CH3 is J, so I is OH, right? So the I in this equation is for OH. So if you look at the equation Ni, so number of OH group, which is 1. So we put here 1. So 1 is more and equal to, so the right side of the equation is Nj. So it is referring to CH3. So Nj in this group, there's only 1. So we have 1 here, and then Uj minus 2. So Uj valence for CH3 is 1. So 1 minus 2 and then plus 2. Okay. So 1 minus 2 is negative 1. Negative 1 multiplied with 1, negative 1. Negative 1 plus 2 is 1. So 1 is more or equal to 1. So it satisfies the first equation for CH3 equal to Sj. That is one thing. Another one, we need to calculate for OH. Now we set OH as J. So when OH is J, so Ni now is for CH3. So NCH3, there's only 1. So you have 1 here. So more and equal to, and this part is for J, right? So J now is OH, right? So Nj and OH is 1. There's only one OH group. And then Uj for OH is 1 as well, minus 2 plus 2. So the same equation as above, so it satisfies the equation. Okay, so all this satisfies only for this molecule. Again, we have only one type, so that is why it's not applicable. Okay, so maybe you can look at the final, the last type of molecule. Okay, if we do it for CH3 equal to as the J compound, then it satisfies. But for CH2, it's not satisfied. So let's look into more detail. So if we set CH2 as J, yeah, so it means that I is CH3, right? So Ni is 1 because there's only one CH3. Is more and equal to what? To Nj. So how many Nj? We have 2 Njs because J now is CH2, right? So we have 2. Multiply with Uj minus 2. So Uj for CH2 is 2, right? So 2 minus 2 plus 2. So 2 minus 2 is 0. 0 multiplied with 2 is 0. And 0 plus 2 is 2. So 1 is not more and equal to 2. So it's not does not satisfy the constraint. Then it is even though one of it satisfy, another one does not satisfy. Even though only one is not does not satisfy, then of course the rule overall is not satisfied. Okay, and then we look for equation number 3. Number 3 is quite straightforward. Just we want to compare the number of the function group with the bound. Okay, sorry. All right. So for example, here for CH3 we have 2. So 2 is between the upper and lower bound that we set. Then satisfy. Then you can check for all. Maybe we can check for this one, OH. So OH, we have 2 OH. So the upper and lower bound that we set is 0 and 1. So 2 does not set, is not between the upper and lower bound that we set. Therefore, it does not satisfy the rule number 3. And for this example, for this compound, for CH2, it follows the lower and upper bound, but for OH it does not follow. Then therefore, rule number 3 is not considered fulfilled, right? And for group 4 also is just a comparison between the minimum of 2 and maximum of n max. So n max is 3, and if you look at the number here, all are between the range. So then of course number 4 all satisfied. If let's say for example you list down another molecule which have four different groups, then of course number 4 will not be satisfied. Okay, and number 5 is just to calculate the number of the groups available in the molecules, and also by looking at the number, it satisfies the minimum and maximum number of the groups that we set. Okay. Okay, so then we can simplify the previous table to be like this. Okay, based on each of the possible candidates, molecular candidates, we identify for which rules it satisfy and does not satisfy, and for any compounds, if only one rules is not satisfied, then of course we consider that the overall molecule is not feasible. So only molecules which satisfies all rules, then only we will choose it. We will consider it as chemically feasible, and we choose it for further for the next step, for the screening step. Okay. Okay, so the number of molecules generated for a larger set of functional groups is enormous, like the example which is shown in this table, right? So we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. So in this example, we have 20 groups in this basis set. So based on these 20 groups, we can produce or we can generate millions of chemically feasible molecular structures. So it's hard to do it manually, right? So we need to have certain rules, and then we can convert that rule into a molecular programming so that we can generate the compounds which satisfies all the rule. Okay, and the list of compound generated would be the feasible compound. Okay. Okay, so next we move on to generation of mixture blend candidates. Okay, before this was molecular structure. Now, after we have obtained the list of chemically feasible molecular structures, then only we can move on to the next step, which is to identify the mixture blends candidate which are stable. Okay, so this is the problem statement. So given a basis set of n molecules, determine mixtures containing m max more than or equal to m more than or equal to 2 that are stable liquid solutions at given condition of the temperature and pressure, and whereby m max is the maximum number of molecules and m is the actual number of the molecules in the solution. Okay, and then we have an example here. So let's say we are given molecules of methanol, ethanol, benzene, and water. So we have 4 molecules. So we need to find stable liquid binary mixture or ternary mixture at 298 Kelvin and 1 atm. So binary means that a combination of 2 compounds, right? Ternary is a combination of 3 compounds. Okay. So the answer is, so these are the stable compound, binary and ternary compound. We have methanol, ethanol, methanol, benzene, ethanol, benzene, methanol, ethanol, benzene. These are examples of stable liquid mixtures. So how to know that these mixtures are stable? Okay, here how we can check it. Okay, so for each mixture, we need to ensure the liquid phase stability. Okay, so the following criterion must be satisfied for all liquid composition, mixture composition. So this is the equation whereby, okay, this is for stable liquid solution. This term must be equal to this term and must be lower than 0. Okay, this is for stable liquid solution, where GE over RT is this equation. Okay, So the details, so delta G is Gibbs energy of mixing. So I hope you still remember the one that you learned in your chemical engineering thermodynamics. And GE is the excess Gibbs energy due to mixing. Xi is the mole fraction of component I. Nc is the number of compounds. And gamma I is the liquid phase activity coefficient of compound A. If you still remember, you can use Wilson, Van Laar, for example, in order to, or you can also use unified model to estimate the value for Y gamma I, right? And yeah, okay. So you need to make sure that the equations are satisfied. Then only the liquid solution are considered as stable. Let's look into more detail. Okay, so the question is easily check for binary mixture to establish miscibility. Okay, so if you need to check for binary mixture, is easy. It says here easy. But if you have multi-component mixture, for example ternary, quaternary, then what you need to do first is that you need to check the binary pair first for miscibility. For example, if let's say you have a ternary mixture of A, B, and C, so what you need to do first, you need to check the stability between A and B, A and C, and also B and C. Okay, you need to check each stability of each binary mixture first, then only you check for the ternary, right? So if any of the pair is found to be unstable, then most probably the corresponding mixture, multi-component mixture, is also unstable. Okay, that is an indicator. Okay, and okay, note that the equation is not a sufficient condition, but only a necessary condition for stability. Right? It is only to check the stability, to make sure that when the compounds are mixed together, then it is miscible. It's not immiscible, right? It does not form like two layers or something. Okay, and also checks at equivalent binary composition are usually sufficient in order to identify phase instability when it arises. Okay. Okay, for example, we have an example here. So which binary pairs in a mixture of methanol, ethanol, benzene, and water are unstable at mixture of, sorry, temperature of 298 Kelvin and pressure of 180 M? Okay, so there are 6 binary pairs which are uh, tested, further tested. So for each pair, an equimolar mixture is tested. So equimolar, it means that the Xi is equal to 0.5, right? And you can use that value. Okay, so when you check it using equimolar mixture for stability, so here are the results. Okay, so this is the result of the stability test, and from all 6 binary mixture, so all satisfy the equation, only for the benzene and water system. So it means that the benzene and water pair is unstable, right? So since this pair is unstable, then most probably multi-component mixtures containing this pair is a strong candidate that it is an unstable mixture as well. Okay, so so the size of the mixture blend design problem depends on the, of course, the number of the molecules, and also the number of molecules which appear in a mixture, right? For example, here in this example, we have 4 molecules, right? For four molecules, we are able to form 6 different binary pairs. We can form 4 different ternary mixtures, and also, of course, since there are only 4 components, we can form 1 quaternary mixture. So basically, for a total of 4 different molecules, there are 11 different mixtures, which are the possible combination, right? But however, since we know that the benzene and water pair is unstable, therefore we can we can identify that only 7 liquid mixed solutions are potentially stable because they don't have the benzene and water pair, but of course they need also to be checked further with only 4 potentially unstable mixtures involving of course benzene and water pair. So basically, if we have more than that, if you have a lot of different molecules candidates that we can consider, then of course the total number of mixture may be very large, and of course we need to have a system whereby or a program or an algorithm that we can use so that we can generate all list of the possible combinations and also check their stability using reliable tests. And of course, in order to do this, we need to use computers, right? Only with the help of computers, then only we can do such calculation in a very efficient way, right? So so even though here in this example we only identify those which are unstable, but when instability is detected in binary mixtures, then the number of feasible multi-component mixture may be reduced dramatically. Like for example here, from 11, 4 may potentially be unstable. Then we have another 7 that we can further check in terms of its stability and feasibility. Okay. All right, I think that's all for generation of the mixture blend, and and of course the detailed calculation on how to use this equation, I'm sure you already know how to use it, right? Because you have learned how to calculate those properties already. For example, the gamma I GE over RT and so on, and that you have learned in the thermo class. And of course later on we will also see how we can in more detail how we can use those equation in the property prediction model part. Okay, all right, thank you.